Alright, so the last section in Chapter 9 that we're going to look at here is graphical solutions to differential equations. Um, so let's make a few notes here. The last section is actually pretty simple. It's something that you've seen in Calc 1 already. It's pretty straightforward. So let's make a note. So we're going to be looking at the first derivative and second derivative here, and from a different perspective. So we can build on our knowledge of how derivatives determine the shape of a graph to solve differential equations graphically. So that's what we're doing here. So these kind of graphical solutions are called phase lines. So a phase line basically is just a graphical solution to an ODE. In this chapter we saw how to solve first order linear ODEs and by algebra or by calculus and algebra. But what we're going to do here is just how do we do this graphically? How do we see long-term behavior of solutions to an ODE? And it doesn't matter if it's an ODE solved with an integrating factor or separable. It doesn't matter. You could look at the solution of the graphical solution of an ODE this way by constructing a phase line. So let's make a definition here. So the first thing we do when we construct a phase line, and this seems very familiar to you, is we want to identify the equilibrium values. So the values of y for which dy dx equals 0 are called equilibrium values. This is something, so basically where the derivative is equal to 0, that's the values of y that are equilibrium values. This is something you've seen in Calc 1, and when we talked about it in Calc 1, we looked at it from a different perspective. We called these critical values in Calc 1, right? Or the derivative is equal to 0. When we did the first derivative test, you might recall that from Calc 1, but since we're looking at it from a different perspective, we're calling this equilibrium values. Okay, so so to make a phase line, for a differential equation, an ODE, here's what we do. So we find the equilibrium values. And we find the equilibrium values for the first derivative and the second derivative. So this is the first derivative, that's the second derivative. Then what we do, and this is very similar to making a, a number line where we find where the intervals are increasing and decreasing and concave up and concave down. It's pretty much identical to that, but we're just looking at it from a different perspective. We're just looking at it in terms of differential equations now, not the graph of a curve. So then, once we find these equilibrium values for the first and second derivative, very similar to that, like you do some test values to find where the intervals are concave up and concave down, and increasing and decreasing. Very similar to that in Calc 1. So then we're going to do some test intervals to determine where the ODE is positive and negative. So just to recall from Calc 1, if the derivative is positive, that means it's increasing. If the first derivative is negative, that means it's decreasing. And if the second derivative is positive, that means it's concave up. And if the second derivative is negative, that means it's concave down. So basically we're just, we're taking what we learned about the properties of a graph, and we're looking at it from a differential equation perspective, and seeing how solutions to a differential equation will change depending on these. And that's what a phase line, or this is also called, phase line is also called a phase portrait. It's also called a phase portrait, but just depending on textbook to textbook, really. Okay, so when we're doing that, so after we do this, then we just sketch some solution curves to see the overall solution behavior to the ODE. And that's basically it when it comes to constructing a phase portrait. This is very familiar to you from Calc 1, and we're going to do it the same way, really. Okay, so let me look at, once I look at a few of these examples, that'll be it for this section. This section's pretty efficient. So let's look at this example here. So draw a phase line for dy dx equals y plus 1 times y minus 2. Alright, so if I want to draw a phase line for that, well, I'm going to draw a number line, right? And I'm going to use that number line. That's going to be the phase portrait. Or that's going to be the phase line for my ODE. I'm going to use this to help me draw a phase portrait for my ODE. So what are the equilibrium values here? Okay, well, so what you're going to do is find equilibrium values. So that's where the derivative equals 0. Alright, so set this equal to 0. Alright, it's easy. So y plus 1 times y minus 2 equals 0. Well, where is that equal to 0? Well, that's an easy polynomial equation. That means y plus 1 equals 0, and y minus 2 equals 0, which means y equals negative 1, and y equals 2. So these right here are my equilibrium values. So I'm going to include them on my phase line. Negative 1 and 2. Okay. So now that I have that, now very similar to what you did in Calc 1, you're going to do some test values to determine where this is increasing and decreasing. Now, before I do that, though, now the order in which you do this is irrelevant, but the way I do it is I find the first derivative's equilibrium values, and then I find the second derivative. So that's the way I'm going to do it. So we have to find the second derivative. All right. And then go from there. So we have to find the second derivative, set that equal to 0, and go from there. But this is the first derivative. So how do we get the second derivative from the first derivative? What do we do? Well, we differentiate the first derivative. So so I'm going to take the derivative of this to get the second derivative. That's pretty straightforward. So I'm going to take the derivative of y plus 1 times y minus 2. All right. Now, so how am I going to differentiate this? Well, you could differentiate this as it is. You could do that. So this is going to be a derivative of a product, so you're going to use the product rule here. Or you could distribute out these terms and then differentiate term by term. Either way is going to be fine. But I want you to understand something here. Since we're differentiating y with respect to x, what kind of differentiation are we doing here? We're doing implicit differentiation. So what I'm going to do here is I'm going to distribute this. I'm going to distribute, or I'm going to FOIL it. You don't have to, but that's what I'm going to do. So I'm going to have the derivative of, when I FOIL this, I get y squared minus y minus 2. All right? So the derivative of that polynomial. So now when you take the derivative of this with respect to x, you're doing implicit differentiation. Right? So when you do implicit differentiation, you're treating this like the chain rule, and then you just tack on a y prime. So when you take the derivative of this, that's what I'm going to do now. So the derivative of y squared with respect to x, so you're going to treat this like the chain rule, and you're going to tack on a y prime. So what's the derivative of y squared? It's going to be 2y times a y prime. All right. What's the derivative of y with respect to x? Well, that's going to be 1, right? And then you're going to tack on a y prime. So that's going to be 1 times y prime, which is just y prime. So you're going to have minus y prime. And then what's the derivative of 2? Well, that's 0. Okay. So this right here is the derivative of the first derivative, but I'm not done yet. I'm not done yet. I want to get this. I want to get this in terms of just y, not y prime. So if I do a little algebra here, if I factor out a y prime, what do I get? I get 2y minus 1, right? Okay, so if I come down here now, all right, so the derivative of the first derivative, so this is the second derivative, all right, but I want to get this just in terms of y. All right, I did implicit differentiation here, and now I just want to get this in terms of y. All right, so, well, what can I do here? Well, isn't y prime right here? It is. This is what y prime is equal to. So what I could do is I could just plug y prime in for this, and then I'll have this in terms of y only. So I'm going to substitute that in for y prime. Equals y plus 1 times y minus 2. So then when I do that, I have y plus 1 times y minus 2 times 2y minus 1. So that right there, that's the second derivative. That's the second derivative. So now I could answer this question. Now I can find the equilibrium values for this. So let me do that over here. So now I can find the equilibrium points for the second derivative. So that means I could set this equal to 0. So I have y plus 1 times y minus 2 times 2y minus 1 equals 0. So where is that equal to 0? Well, this is easy. Y plus 1 equals 0, y minus 2 equals 0, and 2 minus 1 equals 0. So that means y equals negative 1, y equals 2, and then when you solve this for y, add 1, divide by 2, so y equals a half. All right, so these values are the equilibrium values for the second derivative. All right. Okay. So that's what I have now. So if you notice here, negative 1 and 2, they're already equilibrium values for the first derivative. But I have one additional value. I have a half. So I'm going to include the half on this graph somewhere. So a half is going to go, well, so, you know, if I want to be consistent here, so if 0 is somewhere here, then a half will be in between them, obviously. All right. So what I'm going to do is, now that I have my equilibrium values for the first and second derivative all together on the same number line, I'm going to sketch the intervals for the first derivative and the second derivative on this phase line to see which ones are increasing and concave up and down. Increasing, decreasing, concave up, and concave down. And we do that by doing test intervals. All right, so I'm going to take this. So now that I found all my equilibrium values for the first and second derivative, so you find them for the first derivative and the second derivative, I'm going to take this, go to the next page, and do some test values. That's what I'm going to do on the next page. All right, so our curve, so we had dy dx equals y plus 1 times y minus 2, and the second derivative was y plus 1 times y minus 2 times 2y minus 1. And here was our phase line. So I had negative 1, 1/2, and 2. So now I'm going to do some test values. For y prime and y double prime. All right. So just to just to recall, so the equilibrium values for the first derivative were negative 1 and 2. So what I'm going to do is I'm going to do the top portion of this curve as the first derivative, and I'm going to do the bottom portion of this as the second derivative. So negative 1 and 2 was for the first derivative. So for the first derivative, I had negative 1 and 2. I'm just doing this to partition the intervals for each derivative. And for the second derivative, so the equilibrium values for the second derivative were negative 1, 2, and 1/2. So for the second derivative, it breaks up into 3 sections. Negative 1, 2, and 1/2. And that's for the second derivative. I don't put this here because this was not an equilibrium value for the first derivative. It was just an equilibrium value for the second derivative. Right? Okay. So now I'm ready to find test values. So all you're doing now is you're just plugging in test values for each section on the first derivative and the second derivative to see if it's increasing and decreasing. Okay, and concave up and concave down. And then that'll give us the behavior of a solution curve for the ODE, for this ODE right here. Okay, so you could use your calculator for this part. It doesn't matter, I'm just looking for the sign here. So pick a value that's less than negative 1, right? Negative 2, negative 10, doesn't matter. Plug it in here, see if you get a positive or negative value. All right, so do my calculator. So I'm going to pick negative 2, store that in for x, and I'm going to type this in terms of x because that's the variable you can use your calculator. So I'm going to have x plus 1 times x minus 2, and that gives me a positive value. So I know that I know right here that y, the first derivative, is positive because I just found out I got positive 4. So that means it's increasing. All right, now pick a value between negative 2 or negative 1 and 2. 0 is fine. So, you know, that's easy. So when I plug in 0 here for y, so I'm going to have 1 times negative 2, which is obviously negative 2. So that means the first derivative is negative, which means it's decreasing. Pick a value a bit greater than 2, 3. Second enter, and I get positive again. Alright, so now I know, you know, this is increasing, decreasing, increasing. Now do the same thing for each of the 4 sections for the second derivative and plug it into the second derivative. So a value less than negative 1, I'll use negative 2 again. But this time I'm plugging it into here. So x plus 1 times x minus 2 and 2x minus 1. And that gives me negative 20, which means the second derivative is negative. Which means this is concave down. A value between negative 1 and 1/2. So 0 is perfect there, right? So 0, enter, enter. Now I get 2, which means second derivative is positive. Concave up. What's the value between 1/2 and 2? 1. Second, enter. Second, enter. -2. Hey, all right. Second derivative is negative. That means it's concave down. Value greater than 2. 3 works. 20. Second derivative is positive, which means this is concave up. All right. So now that I have, so I did test values, and you could use your calculator for that. That makes it easier. So now you know the behavior of the graph for the first and second derivative in each interval based upon the critical values. So now that I know that, now I could sketch. So now I could sketch some solution curves to the ODE. So the original ODE was y plus 1 times y minus 2. So when you make some solution curves here, all right, you're just basically making a phase portrait. You're making a phase portrait. All right. So when we do this, you're going to draw some, you're going to draw some vertical axes. So let's make this is y. This is x. All right. So the first thing you want to do is you want to include the equilibrium values for the first derivative, because we're sketching the solutions for the first derivative. So the only equilibrium values we're putting on here are the ones for the first derivative. We don't care about, so let me rephrase that. So what are the equilibrium values for the first derivative only? For y prime only. Well, for y prime, -1 and 2. 1/2 was an equilibrium value for the second derivative. I'm not putting that on here. I'm not putting that on the phase portrait. So, all right, well, so 2, well, that's a positive. That's on the positive side of the y-axis. So 2 is somewhere right here. And then -1, right? So that's somewhere down here. So I'm going to put some horizontal lines there because these are equilibrium values. So the function is going to have, basically the solution curves to this differential equation are either going to converge to 2 or converge to -1 or diverge. And that'll classify what kind of equilibrium they are either stable or unstable. So now based upon the phase line that we made up here, now I can sketch some solution curves. So if I look to the left, so let's say I start above 2, all right? So I'm above 2 here, right? So anything above 2. So what's going on above 2? Well, let's look here. So above 2, my function is increasing and it's concave up. Right? It's increasing and concave up. So how do we graph that up here? Well, let's say I started here. So if I go from left to right, I'm going up, and I'm also going concave up. So that means I'm curving up like this. I'm curving up. So it looks something like the following. If I'm increasing and concave up, I'm doing something like that. All right. Now, if I keep going here, so this is still increasing and concave up if I keep going to the left or if I keep going up. This is increasing and concave up on this whole top portion here. So this is a solution curve. All right, now let's look inside the interval from -1 to 2. So from -1 to 2, right, what's my solution to this differential equation look like? So from -1 to 2, I'm decreasing. All right, so I'm going down from left to right. I'm going down, but the concavity changes. So from -1/2, my concavity is up, but this is up, right? But from 1/2 to 2, it's down. And this is down. So all right, so I'm not putting 1/2 on here. I just, I'll approximate where 1/2 is when I sketch it. But so if I'm starting at 2, so from 2 to 1/2, I'm decreasing, but I'm concave down, right? So I'm decreasing. So if I start, I'm decreasing, but I'm concave down. So let's say 1/2 is right around here somewhere. Once I get to 1/2, I'm still decreasing, but my concavity changes. So instead of going like this, I'm now doing this. I'm curving upwards. So if this is like, let's just imagine 1/2 was here, right? So then once I get to 1/2, I'm still decreasing from left to right, but my concavity is now curving upward, as denoted by the phase line. So now, it's starting to do this. I'm still decreasing, but my concavity is now curving upwards. And I'm getting close to an equilibrium value, so my concavity is still going upwards, and it does that for the rest, forever and ever. So, yeah, even though 1/2 is here, right? As you can see here, I'm going down, but my concavity is down. When I go here, I'm sorry, this is concave up, but when I go down from here to 1/2 to -1, or no, this is concave down, but this is concave up. Yeah, concave down from -2 to 1, or from +2 to 1/2, but then concave up from -1/2 to 1. So this is concave up. So that's a curve right there. Let's say I started here. What's it going to look like? Well, if I started here, right, this is still, right, this is still concave down. So the concavity here isn't going to change much. This is still going to be concave down. I mean concave up. I keep flipping that, I'm sorry. Yeah, so the concavity here is not, it's not changing. All right, let's look. Sorry for this little bend right here. That shouldn't be there, because that implies the concavity is changing, but it's not. You can, you know what, on second thought, you can kind of ignore this one, but it's okay. So let's look from -1 below. So from -1 below, I'm increasing, but I'm concave down. So from down here, I'm increasing. So from left to right, I'm going up, but I'm concave down like this. So that just looks like this. Increasing, but I'm concave down. And that does that. And that's basically it. You know what? This should be a little bit more pronounced. Just ignore this part. I'm sorry about that. That was sloppy of me. But once I get past 1/2, my concavity changes, right? So from 1/2 to 2, my concavity is starting to go down. So it's starting. That's where the bend starts. So I was a little premature here. So sorry about that, but that looks a little bit better. That looks a little bit better. All right. So these are some solution curves. These blue ones are solution curves. Each one of these are solution curves. So based upon this graph, you could see the behavior of all different kinds of solutions to this ODE. We've already shown you some ways to solve this ODE, using using integrating factor or separable, whatever. It just depends on what you have. And you could compare that. That's the analytical solution, but this is a graphical solution. And you can use a solution, a phase portrait, to clearly distinguish what's happening to the graph as you keep solving it or keep looking at solutions. So, I mean, except for that little goof there, this is it. This is what you do. And my closing comment here is, what kind of equilibrium is 2 and -1? So if you look here, the solutions, what are they doing to this? Are they closing in on 2, or are they fanning away from it? They're fanning away from 2 here. So this means this is unstable equilibrium. That's unstable equilibrium for 2. And if you look at -1 here, the solutions are closing in from all directions towards -1. So -1 is stable equilibrium. And that's very important when we're looking at -1. So that's very important for when we're looking at different types of equilibrium for, differential equations. That's a pretty important thing in differential equations, is knowing what kind of equilibrium you have, stable or unstable, because that tells us what the values of the function curves or the solution curves are going to trend to in the long run. And that's very important. And, when it comes to making a phase portrait, that's really it. It's really pretty straightforward. I apologize for that little goof there, but that's the basic idea. So that's really it for this section, and that's it for Chapter 9. So what I'm going to do now is I'm going to go on to Chapter 10, and we're going to start a very important subject, which is dealing with series and sequences, and that's very important going forward. We're going to be looking at a lot of that for the majority of the class. So that will be the end of this video.